Okay, let's take a look at our stress example. In our stress example, we're going to look at 3 different options. I'm assuming you guys are following along with the slideshow open beside this on your screen. So the first option is me standing on the ground wearing my Blundstones. I know that I weigh about 600 newtons, or 0.6 kilonewtons. So that's me as a downward force. My feet are being spread out on a surface. I have 2 feet spread out over that surface. I measured the area of my Blundstones. They are about 240 millimeters times about 75 millimeters. I have 2 feet, so I can calculate the area of my feet on the ground. Let's take a look. We've got 240 times 75 times 2 feet. We've got 36,000 millimeters squared. We know that stress equals force divided by area. So we have 600 newtons divided by 36,000 millimeters squared. We can calculate this out, and we have 600 divided by 36,000, and we get 0.01667 MPa. We had newtons, millimeters squared. Newtons per millimeter squared is MPa, which is the units we tend to work with in this. Now, let's say I go into my closet and I'm feeling fancy and I wear my high heels instead. So my force P hasn't changed. So I've got the exact same force, but the area of my high heels probably has changed. I'm gonna say that the heel bit is almost inconsequential and that the toe bit is where most of my load is being carried. We know that that's not completely true. Anyone who's ever walked across grass wearing high heels knows that that heel goes right down into the ground. But let's say that I'm kind of leaning forward just a tiny little bit and all of my weight is just on that front bit of the high heels. So I went into my closet and measured that that's about 100 millimeters by 75 millimeters, and I've got 2 feet. And calculate that out, and we get 100 times 75 times 2 feet, and we get 15,000 millimeters squared. What do you think? Do you think the stress of me standing on the ground in high heels is going to be higher or lower than my Blundstones? Well, my guess is that it's going to be higher because I have a smaller area, that I'm going to feel like I'm sinking down just a little bit more. We know that stress equals force divided by area. We've got the same 600 newtons divided by 15,000 millimeters squared, and we calculate that out. We get 600 divided by 15,000, or 0.040 MPa. So yes, the stress is higher, which makes sense. Now, let's say I'm about to go outside in the winter and I want to go for a walk in the snow, so I get out my snowshoes. So I go get my snowshoes. So these were boots. These were high heels. And these are snowshoes. So again, Shannon still weighs the same amount, 600 newtons, but the area has changed. What do you think? Do you think the stress is going to be more or less? Well, our area, I measured a pair of snowshoes as being 1 meter times 6 inches, or 1,000 millimeters times 150 millimeters times 2 feet. And I get the area of my feet on the ground is 1,000 times 150 times 2, or 300,000 millimeters squared. We need to know that stress equals force divided by area, or 600 newtons divided by 300,000 millimeters squared. And we can calculate that to be 0.002 MPa. That is much lower than our 0.01667 MPa. So it makes sense. Put on smaller shoes, you have more stress exerted on the ground. Put on bigger shoes and you've distributed the same load out over a bigger area, which means your stress goes down. You have lower stress. We're going to jump right into a second example within this. So what is the stress an elephant exerts on the floor if it weighs 44 kilonewtons and its feet are approximately 500 millimeters in diameter? I am by no means an artist. So our elephant's got 4 feet, and we know that his force is 44 kilonewtons. But we know that we're talking about stress. They asked us about the stress here. And we know as soon as we're talking about stress, we like to talk about things in newtons. So let's convert that directly into newtons. We know that his feet are 500 millimeters in diameter. Let's figure out what the area of a foot is. We've got pi r squared, or 3.14 times 500 millimeters squared, or divided by 2 squared. The radius is half of the diameter. We can calculate this and we get 3.14 times 500 divided by 2 squared, and we get 196,250 millimeters squared. We have 4 feet for this elephant. So it's 4 times that. So let's take that 196,250 times 4 equals 785,000 millimeters squared. And we know that stress equals force divided by area. We have 44,000 newtons divided by 785,000 millimeters squared. We can figure out the stress. 44,000 divided by 785,000. We get 0.056 MPa. What Shannon in heels exerted 0.04 MPa stress on the ground. Oh, that makes me feel like I'm kind of comparable to an elephant. That's giving me a bit of a complex there. But let's just for a second pretend that that pesky elephant goes into my closet and steals 2 pairs of my shoes. Let's just take a look at that now. The area per foot is exactly what the area per foot was for a heel, or 100 times 75. Or 7,500 millimeters squared. The stress would be the 44,000 newtons divided by 4 times 7,500 millimeters squared, or 44,000 divided by 4 times 7,500, and we get 1.467 MPa. Okay, so the elephant in heels creates a much bigger stress than Shannon in heels, which makes me feel a whole lot better. He's ruined my shoes, but whatever, the elephant can have them. All right, let's do one more stress example right now as we're going through these slides. We've been asked if steel can bear 350 MPa. So they're telling us that the most it can take is 350 MPa. What force can a 25 by 25 by 25 steel cube support? So they're telling us that the maximum stress is 350 MPa. We don't know anything about that, where that came from, but they are telling us that that's the maximum stress this material could see. We don't want to go over that. They're telling us that there is this cube of material that is 25 millimeters by 25 millimeters by 25 millimeters. And we want to know what that force could be. What's the maximum force? So P max that this cube could support. Well, if we know the maximum stress this material can see, and we know what its area is, we can figure out what the maximum stress could be. We know that stress equals force divided by area. We can rearrange that so that force is stress times area. We want to know what our maximum P is. So we have our maximum stress of 350 MPa times our area, which is 25 millimeters by 25 millimeters. So 25 by 25. So that's this surface area right here. The maximum force this can take is 350 times 25 times 25. Oh, that's a big number, 218,750. But here's the thing, we've been working in newtons and millimeters. So MPa is newtons per millimeter squared, and we multiplied it by millimeters squared. So that gives us newtons. That's great for talking about stress, but now we're talking about a force. And once we're talking about a force, we find it a lot easier to talk about it in kilonewtons. So let's switch this back to kilonewtons. So there's 1,000 newtons in a kilonewton. 1, 2, 3. 218.75 kilonewtons. So if the maximum stress a steel can see is 350 MPa, a little 1 inch by 1 inch cube of it could hold almost 220 kilonewtons, it looks like.